Look up. Our sun, the source of life, shining steadily for billions of years. It feels eternal. But stars have lifespans. Our sun will die. It's a cosmic inevitability billions of years away. But it will be the most dramatic event in our solar system's history. What happens when our star dies? What becomes of Earth? And can humanity survive? Journey billions of years into the future to witness the end of our sun and contemplate our survival. How the sun works now. It's a giant ball of hydrogen and helium. In its core, hydrogen fuses into helium, releasing energy. This fusion pressure balances gravity, keeping the sun stable for 4.6 billion years. Enough core hydrogen remains for about 5 billion more years of stable life. But that fuel is finite. In 5 billion years, core hydrogen depletes. Fusion slows, gravity wins, and the helium core contracts, heating intensely. This heat ignites a hydrogen shell outside the core. Shell burning is faster, producing more energy. This pushes outward, overcoming gravity on the outer layers. The sun's outer envelope will expand dramatically. Its surface cools, becoming redder. Our star becomes a red giant. As it swells, it will engulf Mercury and Venus. Earth's fate is uncertain. It might be just outside the red giant's edge, but the heat will boil oceans, strip atmosphere, and melt rock. Earth becomes a scorching, uninhabitable cinder. Life will be gone. Meanwhile, the helium core contracts further, reaching 100 million Kelvin. Helium fusion begins in the core, forming carbon and oxygen. This new energy source stabilizes the sun briefly. It shrinks slightly from its maximum red giant size. But core helium also depletes. Fusion in the center stops. The carbon-oxygen core contracts. Fusion moves to two shells, helium burning inside, hydrogen burning outside. This double shell burning, AGB phase, is unstable. The sun becomes very luminous and starts shedding its outer layers via stellar winds and pulses, like cosmic coughs. These ejected layers form a glowing shell around the hot core, a planetary nebula. Over tens of thousands of years, this beautiful but temporary nebula expands and fades. The remaining core is a small, dense sphere of carbon and oxygen, Earth-sized but half the sun's mass, a white dwarf. Incredibly hot initially, it will slowly cool over trillions of years, becoming dimmer until a cold black dwarf. Our sun does not supernova. Now, the crucial point for humanity. Our time on habitable Earth is shorter than 5 billion years. Even during its stable phase, the sun's getting subtly brighter. In about 1 billion years, its luminosity increases 10%, likely triggering a runaway greenhouse effect, boiling Earth's oceans. Humanity's survival clock on Earth is 1 billion years. This is immense time, but means survival requires becoming a multi-planetary or interstellar species long before the red giant, likely within 1 billion years. How could we survive? Options are vast and speculative. Leave the solar system. Achieve interstellar travel to habitable exoplanets around other stars. Requires generation ships or science fiction tech. Save Earth. Wildly speculative megastructure engineering to move Earth's orbit outwards. Relocate within. As the sun swells, outer solar system moons, like Europa or icy Kuiper Belt objects, might become habitable or provide resources for habitats. Live around the white dwarf. Construct habitats orbiting the sun's dense remnant. Preserve legacy. Ensure the idea/information of humanity survives via digital archives or automated seed ships sent across the galaxy. The sun's death is on a scale dwarfing human history. Billions of years achieved.